Recording is rolling. It's Friday, September 2nd. So remember today I'm picking up this homework page from you guys. So you guys remember these conceptual questions? We covered these in class. I had you guys just follow along here. And then on the opposite side of this page, there are a few calculation-based questions where you can use these kinematic formulas to solve them. We solved some of these together, and I say just follow along with me and just whichever ones we do in class. All right, so that is what I'm picking up today. You guys got that? Then the other thing that is also out is your guys' open notes take-home quiz. Right? Looks like this. Now we're about to go into a 3-day weekend for Labor Day. So the next time I'll see you is going to be on Tuesday, and then I will pick this up from you guys on Tuesday. Okay? You guys got that? Yeah. All right. What else we got? Okay, I did want to get started on projectiles today, and we'll do a little bit with projectiles. I want to plant some ideas so that going into the weekend, you'll be familiar with some of these ideas, and then next week we'll go more into depth with projectile motion. Yeah, I'm not even quite going to have a 7th period today, which is got to throw some things off, but that'll be all right. We'll deal with that. All right, so projectile motion, we're dealing with the exact same variables and even the same equations as we did for linear motion. We're just taking this into 2 dimensions. So it's the same 5 variables and the same 3 equations, but now it's going to be in 2 dimensions. Here's a classic question, or classic setup. Suppose you have a cannonball at the edge of a cliff and it blasts the cannonball horizontally. Right, land it down here, something like this. Some easy measurements to grab might be the height of the cliff and where the cannonball lands. Right, so call this like 45 meters, call this 120 meters. Just looking at that, do you guys feel intuitively that there is enough information given here that you could solve these questions, you could answer these questions? What is the blast speed of the cannon? And what is the crash speed of the cannon? Do you think that would be solvable? Right? Or you might also have to know the gravity field. Would it be heavily implied that you're on Earth? Right? Because if you change planets, then that would throw these numbers off too. Right? Okay. So today I want to walk you guys through how to solve this. Just again, so you guys get the main concepts and plant some ideas so that next week you say, oh yeah, I'm familiar with this. I've seen at least one of these off. Okay? So key here is that horizontal motion and vertical motion are going to be completely independent of each other, with sort of one exception, and that's however much time it takes for the cannonball to get from point A to point B. The cannonball to get from here to here, it's the same time whether you analyze it vertically or horizontally. But other than that, see, time is a scalar value, right? So scalar values have no spatial direction. But all these other variables are vector values, which means they're either strictly vertical or strictly horizontal. For example, this x for displacement. Well, are we talking about the vertical height change displacement, 45 meters? Or are we talking about the range displacement, 120 meters, which is horizontal? Okay? So vertical or horizontal? Well, maybe I'd have to set up different equations and say, well, am I talking about vertical or horizontal? Okay? Also, how about this acceleration? Guys, which way does gravity pull all the time? Down. Does gravity ever pull right or left? No. Right? Hopefully it's obvious now that I've asked the question. You guys are all telling me, no, gravity only pulls vertically, not horizontally. Okay? And that'll help you set up the equations to go through this problem, solve this problem. Okay? So is it accelerating vertically down this 45 meters? Yeah, because that's the way gravity's pulling. Is it horizontally? Is it accelerating horizontally across this 120 meters? No. If you're up here in a blip watching this cannonball being blasted across the field, way up here in a blip, about a kilometer up in the air, wouldn't you basically be picking up the horizontal component of the motion? Do you guys think the cannonball is going pretty well constant horizontal speed? Right, constant speed horizontally, right? But vertically, it's going, it's picking up speed, faster, 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 picking up 10 meters per second squared. Right? So one framework that I'll give you guys to help you approach a problem like this is to break apart what's going on vertically, the vertical motion, versus what's going on horizontally, horizontal motion. Okay, and you guys know there are 5 variables that we're working with: time, acceleration, displacement, initial velocity, final velocity. Okay. Now, okay, let's also do that for horizontal. Now, horizontal, remember, if it's a projectile, Is there anything pulling or pushing horizontally, right or left? There's not. So is there going to be any acceleration ever? No. Remember, gravity doesn't pull horizontally. And also, we've been ignoring air drag, and that's going to continue. We're just going to keep ignoring air drag. So if that's true, guys, if you set A equal to 0, like no acceleration, you guys remember how that always simplifies down to just that right there? Displacement equals velocity times time, right? So that's the only variables in the only equation we care about, x, v, and t, right? So we got horizontal motion, we got vertical motion, a little wall between those two. Okay, is that idea? Okay. Now I'm going to modify this a bit because that x are totally different displacements. This one's vertical, this one's horizontal. So let me go back and modify some of these variables. So time, that's fine like it is. Acceleration, well, if we're talking about projectiles like free fall, I do know what the cause of the acceleration is, and that's going to be gravity. So I'll go ahead and turn the A into a G, right? This gravity's pulling vertical. Okay. This X, I'm going to change to Y to distinguish it from this character over here. Okay. So I might even call it H. Like over here, I labeled it H for like a height. Height, Y more generally might be some kind of vertical displacement. It could be Y, right? Okay. And then what about these velocities? I'm going to add to the subscripts. So this is initial velocity in the Y direction. This is final velocity in the Y direction. Okay. And then over here on the horizontal side, I'll go ahead and leave XX just to represent horizontal displacement, just like I did down here in the setup. Okay. 120 meters. And I'm going to tag a little subscript X to this V velocity to distinguish it and say this is strictly in the horizontal direction. Okay. And that's not going to change. The entire time it's in flight, it's going across the field at the same speed across horizontal velocity. Okay. Is that okay? Okay. Now, I did give you guys some numbers here, or you might know some numbers, so let's go through and see what we know. Okay. See, I don't know time yet. I bet we could solve that, but save that one. Hey, G, what number should go right here? About 10 meters per second squared, right? How about this Y? Well, on this problem, look, do you guys see the vertical change is going to be 45 meters? Right. Let's call it down positive, so positive 10 meters per second squared. Let's be positive 45 meters for vertical displacement. Let's see. I don't know this stuff yet. X. Do I know X? 120 meters. So from beginning to end, from there to there, the horizontal change is 120 meters. Okay. Is that okay so far? Right. Now, what I'm trying to do is give you guys just one framework to solve projectiles. So it's not the only way to think about it, but I think it helps break the problem apart. Okay. And see what we're getting here is a forest for the trees view of how to solve projectiles. Okay. Because if you only have two vertical pieces of information, like two of those 5 characters, can you solve that by itself? Not 2. You remember you need 3 pieces of information. Right. How about over here? X equals VT. Well, you can't really solve that either. But there is actually one more piece of information you have that I did not write on this piece of paper. Okay, you have to think about this a little bit. Guys, as this cannonball is being blasted from the cannon, is it moving up or down, leaving the cannon? No. So what is its vertical component of velocity leaving the cannon? 0. 0. Do you guys see it? Do you guys see the cannonball leaving the cannon? It's going really fast, but vertically speaking, it's not moving up or down. So what does that tell you? It goes right here. 0 meters per second, right? The initial velocity in the Y direction is 0 meters per second, okay? Because I'm blasting the cannonball horizontally. You guys see that? Okay. Now that you have 3 pieces of information, do you think in principle you could solve for this? Well, you could solve for either of these, couldn't you? Okay. So the time works out to be 3 seconds. Doesn't it take 3 seconds to fall 45 meters starting from rest? You guys remember that from here? 45 meters starting from rest takes 3 seconds. So this works out to be 3 seconds. Hey, do you guys think that, I'll say equals 3 seconds like you solve for it. I'm skipping some steps here because that's what we've been doing the last couple of weeks. Okay. Do you guys think if it takes 3 seconds to get from here to here, that's the same whether you analyze it vertically or horizontally? Yeah. In fact, time is the only scalar value on here. So you can take this 3 seconds and pop it right here. 3 seconds. It takes 3 seconds no matter how you look at it. Okay. Right. And that's the only variable you can do that with because all these other guys are vectors. They have to stay strictly either vertical or horizontal at time. Oh, yeah, that's your scalar. 3 seconds, 3 seconds. Okay. Hey, if you know X and T, can you solve for V? Just divide the two. Guys, what's 120 divided by 3? 40 meters per second temperature. Ah, that's how fast it's going across the field. It's going across at 40 meters per second. Hey, wouldn't that also represent the blast speed from the cannon? That's the answer. 40 meters per second. That's how fast the cannon blasted. It's horizontally, and at 40 meters per second stays same all the way across the field. Okay. All right. Okay. There's a second question here, so let me at least address this question. What is the crash speed? Do you think as this cannonball's falling, it's falling faster, faster, faster overall? Okay. Now, you can see how it kind of crashes on an angle right there. Dig up some notes. Here we go. Here we go. Got it. Okay. Now, as it's crash landing on an angle, do you think it's both going across the field and also down at the same time? How fast across? 40 meters per second? Because that never changed. It was blasted at 40 meters per second. That stays the same. It's 40 meters per second. Now, how fast down? You guys remember at 45 meters, it takes 3 seconds to fall? So it's falling vertically for 3 seconds. How fast does it pick up to vertically? 10, 20, 30 meters per second. That's remember V equals to GT. Right? So it's going 30 strictly down. 40 across, 30 down. Doesn't that look exactly like this? 40 across, 30 down. Can you do Pythagorean theorem to put it all together and get 50 meters per second? Right? Right? Guys remember that? Okay, guess you did that, right? Okay, so that's a quick crash course intro to projectiles. Yeah, we'll do that more later, but I'm recording this in a video, so this will all be on Google Classroom if you need to see that explanation a second time. But let's go ahead and close out this week with just some linear motion questions. So I have an activity for you guys that involves stopwatches. Do you guys have your cell phones up? Okay, so pull up the stopwatch function on your cell phones. Stopwatch function on your cell phone. Because I'm going to have you guys calculate what the drop height of a roller coaster is. Let's get a roller coaster going. Roller coaster. Is my little roller coaster parked right up here? Okay, so ready to crash down? Okay. Suppose that it's going extremely slowly or basically starting from rest. Can you say that the velocity up here is about 0 meters per second? Okay. Now, it might be an estimate, but it might be close enough to answer this question. Okay. And do you see how this is almost vertical? In fact, it's so close to vertical, you could probably approximate it as a pure free fall and get this pretty close. Okay. Suppose you want to figure out, I wonder what the drop height is. What is that height? Okay. Based on the falling time, do you think you could do that? If you know how much time has passed, do you think you could calculate what the drop height is? Okay. We're about to go on a roller coaster ride. You guys got your stopwatches up? Well, let's see. We're not ready for that guy yet. Let me get here we go. Are you guys timing yet? No, because he's not in free fall. All right, so wait just for the free fall portion. Just wait for the free fall. Oh, geez. All right, I'm gonna do a couple more because that probably good trial runs. All right, so see how many seconds you got. Drop that number down. Let's do a couple more runs here. Let's do one more time. One more time. Oh, geez. All right, let's switch back over here. Switch back over. So that kinematic equation might be helpful. All right, so you guys have some drop times, right? I'm going to see if you guys can do the whole thing. Okay. Somebody tell me what they got for the height of that roller coaster. What'd you get? That was Yeah, work on that. Who's gonna get this? Who's gonna get the height of that roller coaster? How about this? What was the fall time? Who at least got a time? Yeah. What kid? You got what? Here. Let me help you guys out with the drop time. Let's go back over here. Yeah, what you got?
198.
It was 198 meters. Huh. Okay. Sounds a little bit big too. How about this? Let me help you guys out here. So we're not timing yet. Not timing yet. Not timing yet. No free fall yet. Go front. There. I mean, pretty close, right? Few seconds. How many seconds is that? About 3 or 4 seconds. Yeah, I'm looking at about 3.8 seconds. 3.8 seconds. Okay. Who can tell me how far that thing would fall in 3.8 seconds? What formula are you guys using? What'd you get?
72.
72 meters. That's it. That's it. Yeah, and we got it. 72 meters. So we're going, the height drop is 1/2 GT squared. I guess it's a modified version of this one, right? If V not 0, this piece goes away. Goodbye. X, we're talking about the height for displacement. Okay. Acceleration is gravity. You guys see how this is this? Okay. So let's do 1/2, about 10 meters per second squared, or maybe use 9.8. That's fine too. 3.8 seconds squared. Yeah, that should be 72. Let's see if it is. 72 meters. Okay. And that is the answer. 72 meters. Hey, you guys want to do the tallest roller coaster in the world? Let's screen back over here. Let's do the tallest roller coaster. Now, have somebody tell me what's the tallest roller coaster in the world.
5, 4, 3, 2, 1.
That was a good practice round. Let's do this again. All right, scroll bar. Here, let me get rid of that. All right. Let's do one more time. All right, one more time. Here we go. All right, you guys get some times on that? Cover. So it's like the same math, right? There should be a longer time. What was the time you guys got?
4.5 seconds.
4.5? So, all right, so that's kind of close. Yeah. Let's run 4.5. You guys get 4.5? So if you got 4.5 seconds, so that would be about 101 meters. Okay. Since I know what the ideal answer is, let's say the ideal time would have been about 5.3-ish seconds. Let's see what that works out to. About 140 meters. Okay. The textbook answer, by the way, is 139 meters. Okay. So if you calculated a height drop for that one and got 139 meters, then that would have been perfect right there. 139. Let's do some more calculation from video. How many guys have ever driven along I-95 and seen one of these? Oh, we got right there. You guys seen one of those? Yeah. So that is called an attenuator. What would that be good for? Why do they build those around? If you crash into it, right? So, do you guys know how on the roads in the states how many fatal crashes there are every year? How many people die from car crashes in the states every year? It's about 40,000, and that number's been pretty consistent for a few decades now. About 40,000 a year. Okay. We have one of the lesser known stats, but pretty good to know, right? So there could be all different reasons you crash. Maybe there's bad traffic, you're distracted, you're tired. So one way or another, you drift off the road a little bit, and bam, you guys want to slam into this concrete barrier. Ooh, probably a bad day. Maybe your last day. But if you slam to this attenuator, is that going to maybe extend the time or the distance of that collision? Yeah, and say why would that be good? Well, let's think about from a physics point of view, just with those three kinematic equations that we have to work with, what would change and why that would be more helpful to slam into that attenuator, right, from that point of view. You use other physics to say it, other points of view too. But say what's changing? Hey, whether you slam into like the bare concrete or the attenuator first, either way, what is your final velocity? Zero, right? You're coming to a stop either way, right? What do you think your initial velocity would be? Maybe just like however fast you're driving, right? Highway speed, do you think maybe about 70 miles an hour? I-95, right? By the way, that works out to about 30 meters per second. So when I run the numbers, we're going to do that. Maybe 30 meters per second. Okay, so it looks like we have some numbers that are locked in place regardless of what you're running into, right? You have initial velocity and final velocity. So those are going to be the same. Okay. Looking at that green poster up there, think about this. Now, the T time, I want to kind of avoid that sort of for the, although it is true that the time of collision would be extended, and that would be good. But that's going to be a tiny fraction of a second either way. Right? So it's like, But I can definitely see the change in X, right? The difference in the displacement for the collision. Okay? And that's going to affect the acceleration. Hey, those kinematic variables up there, which one is the one that you feel? You can feel accelerations. You guys remember that? You feel accelerations, right? Okay. So I bet if you came to a stop in a real short time period, that might correlate to a very large acceleration. And if you extended the collision over a long distance, that might decrease the overall acceleration. You guys think? Okay. Let's try this out. So go back over here. Okay. What I'm whoops, flip the screen. What I'm trying to get at is, I think the formula that I want to use for analysis is going to be this very last one. Okay, because you guys know what the two V's are. This one's going to 0. This one is your driving speed. And that's regardless of what you're running into, right? Those two numbers are just locked in place. Okay. But these two guys right here, see, if you slam into that concrete barrier, from the point where the front of your car starts to make contact with that concrete barrier to the point where your car comes to a complete stop, what's a good estimate for what X might be? From the front of your car starting to hit the barrier to a complete stop. Here's 1 meter, 1 meter stick, right? Meter stick, meter. Okay. How many of these do you think from the car starts to touch the concrete barrier, goes complete stop? What do you guys think? But four might be the whole length of the car and turn to dust. Maybe 1 or 2. Do you think maybe 1 or 2? I guess if you're being generous, maybe 2. Okay. Let's do that. Let's call this like 2 meters. Right? Do you think you could calculate what the acceleration is going to be, which has something to do with something you would feel, which might have something to do with how bad the collision is? Okay. Let's run the numbers. So I got final velocity squared equals initial velocity squared plus 2a solving for x. Okay. Going to 0 from highway speed. So 70 miles an hour is a little over 30 meters per second, probably about that. We're trying to figure out what's the rate that you're slowing down, so acceleration. And we're giving ourselves about 2 meters to come to a complete stop. Okay. Guys, what's 30 squared?
900.
900. Okay, subtract that over, say negative 900. Then 2 by 2 is 4. What's the last algebra step? Divide both sides by 4. So I'm getting acceleration of negative 220 something meters per second squared. Okay. So now we made up some estimates for what these numbers could be, but they might vary a little bit. But in the big scheme of things, it looks like about 200 some meters per second squared. Okay, great. That's a big number. What does that kind of mean, like in context? Hey, are we in an accelerating field right now? One Earth gravity, one Earth gravity. And how many meters per second squared is that? It's 10, right? Think we could do a little railroad track dimensional analysis on this and get how many G's this is? You guys ever heard of like G-force, right? Which is really more like an acceleration, but that's what we're about to do right here. You guys think every about 10 meters per second squared represents 1 Earth G, like 1 G-force, 1 G? You guys remember these railroad tracks, dimensional analysis? Is that going to be about 22 G's? 22 G's? Okay. Hey, how many G's can the human body withstand before it's like, well, yeah, how many can you go up to? Let me give you guys some video context on this one. All right, so, and then we'll go back and see what it would have been if you slam into the attenuator. Because we know slam into concrete, it's about 20 something G's, right? Let's take a look at a centrifuge here. Okay. You guys see it's a NASA centrifuge for, well, to train astronauts. Could you guys imagine if you're sitting in one of those boxes, what that would feel like, right? It looks kind of like an amusement park ride, doesn't it? Right? Do you think if this thing is big enough and you're walled around and you're just like sitting at rest, well, you think you're at rest relative to the box. Can you even detect any rotational motion? Probably not. Probably be really hard to tell the rotation unless you just like started walking around. Do you think you would feel like you were being thrown back into your seat? Kind of like if you were in a car slamming on the gas pedal and vroom, accelerating forward, right? So isn't this like a way to like simulate accelerating forward? Right? NASA astronauts, by the way, get up to about 6 G's, or about 60 meters per second squared as they're blasting up. Right? Let's go inside one of these. Let's go inside.
Cool. It's ready. I'm ready.
See a G counter up here? 1 G. He's at 1 G right now, right? You're in 1 G. He's in 1 G. Not for long.
2, 1, engage. Leg play, deep breath. You're on top. 3, 1, 2, 3.
9 G's.
1, 2, 3. Squeeze the leg, squeeze the butt. Hey, squeeze, keep squeezing, keep squeezing, keep squeezing. Are you there? How you doing? How you doing? No. You know what happened? No, I don't.
Nah, he blacked out. G-lock. Yeah, so he got up to 9 G's, but 9 G's, well, you have to have a special astronaut training. You got to squeeze your legs so the blood doesn't pull. Got to wear a special suit. So 9 G's looks pretty dangerous, doesn't it? In fact, if they left him there for like a half hour, well, probably not come out looking too pretty. So this crash is looking like 22 G's. Yikes, that's like 2 or 3 times that. But this is only a fraction of a second, so maybe there's that. Yeah. Let's try out that attenuator. So what's that attenuator going to do? It doesn't change that. It doesn't change that. It does directly change the distance of the collision, doesn't it? Right? What do you think about how long do you think that attenuator was about? How many meters? How many of these meter sticks? About how many? I'm thinking probably a few of these, right? Here, let's call it about 6 meters. Let's say it triples the distance, right? Just to come up with a number. Okay, triple the distance. Let's go final velocity squared equals initial velocity squared plus 2ax. I'm going to plug in all the same numbers except I'll do triple the distance. So we're going to rest. from highway speed. We're solving for what's the slowdown rate. And we're going to go up to 6 meters, which is triple of the 2 meters. Okay. 30 squared is 900. Divide by 12. I'm looking at 75 meters per second squared. Okay. And if you like, let's put that in, how many G's is that? So about 10 meters per second squared per 1 G. Is that about 7.5 G's? The number's negative too, but the magnitude, I guess, would be about that, right? So now let's do a side-by-side comparison. So bare concrete wall, we're up to like 20-something G's. With the attenuator, we're down. Oh, hey, this looks like within reasonable range, right? Actually, this is pretty close to what you guys just saw in the video, except it's only a tiny fraction of a second, right? Okay, so this looks a lot more likely to live. Did you guys see if you triple the distance of the collision, you get about a third of the acceleration? Is that, that looks like a straight inverse relationship going on there. Okay. Yeah. Okay. Well, let's do one more thing because we got about 3 minutes. I think we got just enough time for this. Let's do let's see what's this guy's collision right here. All right, so let's go back to 1990. There's a bad collision here, but this guy ends up being alive, by the way, so he's okay. Bam. Okay. Now this NASCAR race, how fast do you think they're going? Do you think about 2 or 3 times highway speed? Maybe. Let's call it maybe twice highway speed. Right? And do you think this guy comes to a complete stop in what, maybe a couple of meters if you're generous? Maybe a couple of meters? All right. So let's flip this back over. Let's see what the G force is on this guy. Okay. Again, he ended up being perfectly fine, so pretty lucky guy. Let's go final velocity squared equals initial velocity squared plus 2AX. Okay. Now remember, if you triple that distance of collision, you get a third of the G's. Okay. What if you, I know it's a double, let's do triple, just so you can see what happens if you triple. What if you triple your speed? I know this is still 0. I don't know how fast he was going, but let's say triple highway speed, which should be about 90 meters per second. That's probably an overestimate, but I like the fact that it's the same factor. It's like a factor of 3, right? Because it works out differently. The fact that it's being squared works out differently. Okay, put about 2 meters here. Right, 90 squared, that's 8,100. Subtract that over. Divide by 4. Looking at 2,000 meters per second squared, or you could call that about 200 and some G's, about 200 G's. I think that's an overestimate based on what was there, but about the right order of magnitude. That's what you might call a back of envelope calculation based on video evidence. Yeah, so it's upwards of about 200 G's. Now, since it was only a fraction of a second, all right, living, but yeah, I'd like to walk away from that one. All right, we got about 30 seconds to the bell. You guys got any questions about anything? All right, so you guys all turn in your homework. All right, and that is our wrap on the week.